Okay, so hey guys, welcome again with the Leetcode daily challenge, and let's get going with it. What we have today. Okay, yeah. So we have the number of ways to arrive at destination. You are in a city, again a graph question, I guess. Yeah. You are in a city that consists of n intersections numbered from 0 to n minus 1 with bi-directional roads between some intersections. The inputs are generated such that you can reach any destination from any other intersection, and that there is at most one road between any two intersections. You are given an integer n and 2D integer array roads, where roads I is equal to u to v to time means from for reaching u to v it will take time, this time, okay, this much time, and you want to know in how many ways you can travel from intersection 0 to intersection n minus 1 in the shortest amount of time. Return the number of ways you can arrive at your destination in the shortest amount of time. Since answer may be large, return it modulo 10 raised to 9 plus 7. Got it. So see, if uh, if you have study about graphs, there are certain algorithms for these kind of questions, and here we can see that we have to find the number of ways to reach from start to end to reach a destination in minimum time. Means these, we can consider these times as weights. With minimum weight we have to reach the destination. We can relate it to algorithm, a really famous algorithm, that is the Dijkstra algorithm, which uses min heap or priority queue to solve such a situation where we have to reach from a start to end using in minimum time or in minimum weight, we can say, because I have studied that algorithm in weight terms. But yeah, that's same thing. So yeah, that's the thing. And here we have to maintain one more thing, is the number of ways we can reach at destination with that minimum time. Okay, so what we'll be doing is, initially let's just form the adjacency list. So vector of pair int, let's take long. Okay, long long adjacency and of size n, fine, for a not end for auto of r for the roads, adjacency of r0 dot pushback a pair which will be r1 and r2. 2 is the weight, 1 is the destination, and it's an undirected graph, so we can do this thing, that r1 to r0 will also have r2 weight. Perfect. Yeah, so after creating this adjacency list, let's create a priority queue. Means a min heap. Okay, max heap is a simple priority queue int, that's all. But for min heap, we have to do some extra things like long long, then vector pair, and then greater. Yeah, I don't exactly remember, but it was something like that only. And greater pair long long, that will be the PQ. Okay, and we will start from 0. So see, this priority queue will store two things. I guess for the priority queue, for inputting the values, we use push, or what we use, I guess we use push only because it's a kind of queue only. Okay, we will push here and we'll push a pair here. Now see, priority queue will contain, main reason of using the priority queue is to extract the minimum time. Okay, so first value will be time. For reaching 0 we will consider 0, and 0 is the node. Second value will be the node value. Okay, what we have as the node value. Okay, yeah. So yeah, after that, what we will do is, yeah, let's take a distance vector because we are using the Dijkstra algorithm. So it's the basics of it. You can study about it to for like more details about this. That will be the distance, and it will be of size n, and initially everything is far. Okay, because we are going to compare the distance we'll get to this initial distance, so it should be the maximum such that that distance can be updated. That's why we're taking it as maximum. And for reaching 0, the distance is 0. And another vector we will take in this question is the ways of reaching at some point, from some point in minimum time. Initially ways for everybody is 0, but ways for 0, let's update it to 1. There's one way to reach 0 because there gotta be some way, otherwise how can we do this question? Okay, and yeah, so let's start processing this priority queue. While this is empty, we will take the initial thing whatever we have in that. So it will be auto f is pq dot front. Oh, no, not front, it will be top, and then pq dot pop. Now the node is what and the time is what. See, first thing, time is the first thing. Okay, f dot first, and long, only one long we can use. Long node is f dot second. Fine. Okay, we have this now. Now we will go to each of the neighbors of the current node. Okay, we will go to those neighbors. We will see that is there a path to these neighbors, that particular neighbor, from anywhere else which has a less time than the current. If it has, then we will do nothing. Okay, and if the current time is lesser than any other time it have already reached, someone has reached from there to there, then we will update the time. Okay, we will get it what I'm saying, that firstly let's iterate through the neighbors of it. That will be adjacency of this node. Okay, adjacency of this node. Fine. So now what have we stored in the adjacency list is this second node and the distance. Okay, destination and the distance. So the destination node, we can take this as the maybe, yeah, destination node. Destination node is this it dot second, or yeah, first, and second is the time. So long destination time will be it dot second. Now we'll compare the time. If this time we have used to reach there, destination time plus the time for reaching that earlier node. For reaching 0 we have 0, but for future cases we have to take the time. Okay, if that time plus the destination plus that particular edge time is less than the time of, basically, yeah, distance time, that's the same thing actually, because we are considering distance as that point. That's variable array for time. If it is less than the destination actually stores the minimum time. Distance actually, this array actually stores the minimum time to reach that particular node. If the distance of this node, if this condition satisfies, then we will update this, that dist for dash node will be now equal to this specific value. Okay, this specific value, and we will push this in the priority queue, dash time and dash node. Okay, fine. And the ways of this dash node will be equal to the ways of this node actually. See, whatever are the ways of reaching 0 will be the ways of reaching 4 for the time 5. Okay, it will be right, because one way to reach 0, then one way to reach 4 also for now. Later we will have other options also. Wait a second. Yeah. Now, if the time is equal, if we get the same time that we have got earlier from some other way, then the ways is increased. Nothing else we have to do, just the ways are increased. Okay, if else if the time plus the dest time got equal to what, the adjacency, sorry, the dist of the dest node. If that these are equal, then obviously we will just increase the ways of the dest node, and that will be equal to plus equals to, but there can be multiple ways, so we will have to provide a mode there. Percentage mode we have to write, right? Let's do this, and long that is equal to 1e9 plus 7. Perfect. And there will be though the way we already have, plus the ways we get to node, those will be added for this point now, and else we have to do nothing. So we just have to return now the ways to reach and minus one node, and percentage can do mode. Yeah, I guess that's pretty much for this one. It's an easy question, like if you know that how to do this using the digest algorithm. Otherwise, it may take time to reach there. Okay. Yeah, we can. Let's take long actually. Will it run fine now? Int and can't we use it here? Anyways, no worries, we can put it inside a vector. Yeah. की बेटी बिगड़ी हो तो समझा. Okay. Okay, this should be mode actually. Okay, mode. Let's shift it out here, and I guess that's it. Okay, we got a wrong answer here. That is expected is 4, but we have got 3. So with the answer of 7, it should be 4 paths, but we have just got 3 only. And what could be the reason for it is, if see, we have pushed 0 0 initially, fine. Okay, ways initially 0, long max, for ways for 0 is 1. Then we go to priority queue, take the top of it, then pop it, stores the node and the time, and time is it dot first, f dot first, and f dot second. For it now, it dot first is the node. It dot first, yeah, perfect. And the destination time is the second. Now the destination time plus the earlier time is less than the dist value of this node destination. Okay, it should not be. Yeah, it will be not obviously this one. Mm-hmm. And then ways of dash node will be equal to ways of node. Okay, pq dot push. Okay, wait. Not dash time actually. It should be dash time plus time actually. Yeah, updated value of this dash node must be there, right? So it must be this or this value. We can put out here. Control C. Perfect. Let's try submitting this. Exactly. Yeah. So this was the question for today. That's the 4 consecutive day for the graph question. But yeah, that totally Dijkstra algorithm question. Nothing else. Like you can do it if you have done the Dijkstra. You can do it otherwise also, but it will take some time to follow up on the things we need to do. Yeah. So that was it. Uh, so again, a small summary is that we need to find the number of ways to reach from 0 to the last node n minus 1 in minimum time. We have to count the number of ways to do that. Now, for reaching from one node to another in minimum time or with minimum weight, we use an algorithm to determine that, and that is Dijkstra algorithm. Dijkstra algorithm basically uses a min heap or a priority queue to filter out the minimum time taken to reach a particular node, and we store that in a vector which we have taken here as dist. We will store for each node the minimum time to reach there. Okay, and we will take additional vector ways, which basically means the number of ways to reach that particular node, ith node, in its minimum time. Okay, it has a minimum time to reach there. Now what is the minimum, how many ways are there so that we can reach in that node in minimum time? Maybe there are multiple ways to reach that node in the same time, and that is the minimum time. So that's why we have used a ways array. Like here 0 to 6. Yeah, for reaching 0 to 6 we have 4 ways, 5 ways basically. 1 2 3 4 and 5 ways. But 4 ways take 7 minutes, and the other way, remaining way, is taking more time. So that's why there are 4 ways to reach here in minimum time, that is 7 minutes. And how we do it now is simply like go to the next node for 0, one by one, all the neighbors. We will go there. We will check that is there any existing minimum time which is less than the time we have took. If it is their minimum, then we will do nothing. If our time that we have taken right now is less than the earlier time, earlier recorded time, that is initially long max. That's why we took long max. Okay, now you got it. So if it is less than that recorded time, then we will update that time. We will update the dist vector, and we will update the ways vector. Like obviously for reaching 4, if there was earlier a way but it has more time, now we'll update the time, this one with 5 and number of ways to reach 4 in that minimum time is same as the number of ways will reach 0, right? It's just the next node. But if the time is equal, now we have some more ways to reach 4. We had earlier ways to reach 4, but now we have some additional ways through 0. So the ways will be added now for that 0th node, and for rest of the nodes we have earlier when the time is equal, and rest we don't know nothing. And then we'll just return the number of ways to reach n minus 1. Mode is we're taking because the answer can be big number which is out of bounds for the even the long. That's why we take it, because it is suggested in the question. That's why we take it. Fine. So this is the question for today. Again, not really hard. If you have done the basics of graphs and the algorithms you know of, that will be easy. Otherwise also, like yeah, kind of we can say medium or medium to hard, maybe that kind of question if you don't know about the algorithms. But if you know about it, then it will be not too hard for you. So that's it for today, and we'll again meet tomorrow.